Hello and welcome to a chapter on how data is transported over the network. So we are specifically going to talk about excuse me, we're going to talk about the transport layer, layer 4 of the OSI model, and then we'll get into towards the end. We'll talk about the routing protocols, the different types of routing protocols, what they are and what they do, and how do they find routes the best path to the destination. And finally, we'll talk about some troubleshooting utilities, commands that you can use to pinpoint where the problem might be. Just a little warning: in this chapter, you're going to do a lot of writing. So again, take your time. You don't have to finish this whole thing in one sitting. So just maybe every 20 minutes or so, take a break. All right? All right, so let's begin. When it comes to the TCP IP, if you remember from our previous discussions, when you want to send data or you want to use an application, any type of application such as email, telnetting, downloading a file, or accessing an HTTP file, your data is going to be converted into what we call data or payload. That goes through the first three layers: application, presentation, and session. Then it's passed to the transport layer. The transport layer takes the data from the top and converts it actually breaks it up into little segments. If TCP took it, it'll break it up into segments. If UDP took it, it'll break it up into datagrams. And then what you do is you attach port numbers to the segments and the datagrams. And there are other things that happen, which we'll discuss in a few minutes. Then those segments, once you attach the headers on them, they become segments, you pass that to the network layer. So this whole segment is passed to the network layer where IP resides. IP attaches, for example, the IP addresses on it. And those IP addresses are, you can call them the header. This whole thing becomes then a packet. Then the packet is given to your NIC, where NIC will attach the headers and the trailers to it, and it becomes a frame. And then the frame is thrown on the physical wire. It's sent across, and on the other end, you receive it on the physical layer. You open up the frame, pull the packet out, and once you pull the packet out, you can open up the packet, pull the segment out or the datagram, and then you pull the datagram out, open it up, and you can pull the data, for example, right? So this is how it works, the encapsulation process of how you do data. So we will talk about specifically how TCP, IDP, UDP works. We'll talk about the address resolution protocol as well. So as we've discussed later on, previously, Layer 7 is the application layer. That's where you create the data, the payload. Then you've given it to Layer 4. It's not that we specifically skip the presentation in the session. It's really they're all together. Layer 7, 6, and 5 do the same thing. The protocol, for example, SMTP does everything that Layer 7, 6, and 5 did. Then Layer 4 takes over where you have TCP and UDP. And they create a segment. That's where your port numbers come in, right? Layer 3 adds the IP addresses and becomes a packet. At Layer 2, you take the packet and you add the MAC addresses on it, and it becomes a frame. And then on the physical layer, that's actually where you put the data on the wire. All right, so here's a couple of things I want you to write down. A switch is a hub, which is not here. A hub is considered to be a layer 1 device. So write that down. A hub is a layer 1 device, which means a physical layer device. Because it just connects every bit that comes in is sent to every other connection to anywhere on any connection to the network. The switch is a layer 2 device because it moves frames. Remember, frames is a layer 2 data. Router is a layer 3 device because it moves packets. It works with packets. A firewall is a layer 4 device because it looks at the port numbers, for example, in addition to the IP address to either block or permit data or segments from coming into the network. A lower router can act as a firewall too. So, for example, a router does what a switch does, and also at the physical layer. So the higher you are in the OSI model, you actually do all the jobs that are underneath you. All right, so let's talk about TCP. You know what? Here's what I'm going to do. So I want to go back over to this, and I want you to write everything that is written here. I know I typed this down, so because I want to discuss it. Let's talk about TCP operations. The transmission control protocol. So I want you to write this down while you're listening. You can pause it and just type. So when data is received from the upper layers, the first thing that TCP does. Remember, there's only TCP and UDP operating at the transport layer. So when the data is given to the transport layer, TCP will grab data. If the application layer is SMTP, POP3, IMAP, Telnet, SSH, HTTP, any of those, they always give their data to TCP. They don't give it to UDP at the transport layer. So when TCP grabs the data from the application layer, the first thing that it does is it's going to break up the data into little pieces called segments. Why does it break them up? Because it knows there's only a certain amount of data that can be encapsulated in a frame. And that includes all the headers, all the IP addresses, the port numbers, whatever you need to encapsulate the data with. Once it reaches the NIC in the frame can only put in 1,500 bytes. So here's something to remember. What is the maximum packet size that can fit into an Ethernet frame? The answer is 1,500. The minimum is 46. That's, by the way, called MTU, Message Transport Unit. So the maximum MTU that can fit into an Ethernet frame is 1,500. So anyway, at the transport layer, what it's going to do is it's going to take the data from the upper layer and breaks it up into little segments. Then each segment is given a sequence number, so that's called sequencing. So to be able to enable the receiver to reassemble the data. For example, this is segment number 1, segment 2, 3, 4, 5, 6, 7, 8. So when you send them out, the receiver will be able to put back the whole thing together, to put back the data. After you stamp the segment on each one of them, then what you're going to do is you're going to put port number on each of the segments. A port number identifies what type of data was given to you. So when somebody looks at the segment and he sees port number 25, it knows the data that's inside that segment is an email message. All right, and then number 4 is the first thing that it does. Now the segments are ready to go. So we call TCP connection oriented. What that means is before it even sends out data, TCP reaches out to the receiver and gives them a call. Tell them, are you there? So what they do is they create a 3-way handshake technique. The sender will send a sync signal to the receiver. The receiver will send back an acknowledgement, and the sender then will acknowledge back that acknowledgement. That's called a 3-way handshake. And this is like before you go to a friend's house, you give him a call just to make sure he's there. You call him, he answers back, he says, yes, I'm here, and then he says, okay, now I'm going to send you data. That's connection. If the receiver does not acknowledge your sync signal, then you don't send any data. So that's what we mean by connection oriented. TCP is also reliable with flow control. What it's going to do is it's going to send you that first segment that has sequence number 1 on it, and it's going to wait for you to respond back, to give you an acknowledgement that the data is okay. data is fine, segment number is fine. Please send me 3 more segments. So you send 2, 3, 4. Let's assume there's 10 of them. And you wait for the receiver's acknowledgement. Let's say you receive back and it says, okay, the 3 segments that you send me are good. I'm not that busy. Send me 5. So you send them, 5, 6, 7, 8, 9. Okay, maybe number 8 got corrupted on the way. So the receiver will tell you, I received up to number 7 was good, but we're going to slow down a little bit, send me 3 more. So you'll send them back 8, 9, and 10 again. By the way, if 8 was corrupted, you're going to have to send 8, 9, and you don't even look at 9. You have to resend it again. Right? That's reliability and flow control. You're controlling the flow of the data. The receiver and you are constantly talking to each other to either increase or decrease the amount of data that has to be transmitted. Reliability comes in. You're going to make sure the receiver tells you that all the data is good before you close out the connection. Right? You're going to make sure that all the data that's being sent is received. That's what reliability means. So TCP is a connection-oriented, reliable with flow control. Right? Be in more details. So what you need to send out, let's say here's the first segment that you send out with sequence number 1. The source port number, you make it up from the dynamic ports. Remember the 3 types of ports that are out there, so I put that in there. The destination port is 25 because the data in here is email. So I send out this first segment, this segment sequence number 1 on. So what you're going to do, if this is what I receive as an acknowledgement from the receiver, he says acknowledge to Windows 3. So what I'm going to do is he's telling me send me 3 more segments. That's what the window size means. With acknowledgement number 2, starting with number 2. So that means number 1, sequence number 1 was good. So I'll send him, remember I said, send him number 2, 3, and 4. That's the next 3. So he receives them, and if everything's good, he'll send me back saying, if the next window size, he says 5, an acknowledgement 5. Right? That means send me 5 segments starting with number 5. That means the first 4 were good. Right? And so on. Alright, so that's how TCP works. Transmission Control Protocol. We are controlling the transmission of the data. And it's reliable. UDP operation on the other end. Typically UDP works with inside the LAN. If your data is going outside your LAN, most likely you're going to use TCP. And most applications that connect out to the internet will use TCP to make sure that the data is reliable and it reaches the destination. But if you are directly connected to a switch or a router inside the LAN, or like the DHCP server, you're going to use UDP for quick, fast connections. You're directly connected and you don't need to have that reliability because that creates some sort of a delay. So when, for example, DHCP from the upper layer gives the data to UDP, the first thing that it does is it breaks it up into little pieces called datagrams, and you put the port numbers on it. No sequencing. Alright, you put the port numbers on it, and that data is sent directly. Immediately direct. That's it. Just port numbers is placed on the datagram and you send it. So, UDP is connectionless. They don't make a phone call, they don't send a sync signal, the three-way handshaking. So it's connectionless. Unreliable. It's not going to make, the receiver doesn't talk back to you to let you know that the data was received successfully. And no flow control. There's no sequence numbers on it. And by the way, this is a problem for voice over IP, even though they love to use UDP because of the sequencing problem. That's why we have RTP, the real-time protocol that does the sequencing before you use UDP. This is called RTP is used to fix whatever UDP does not do in terms of sequencing. If you want to use it for voice over IP. All right, so that's the operation of UDP and TCP. So let's go back. Please write this down. Now you can use this to complete, whatever other notes that I asked you to do. You can come back in here and type. All right, so go on back to the notes. Here is the TCP segment. This is all the labels that are stamped on the TCP segment. This is the destination port. Remember where I put port number 25. The sequence number, if it was number 1, the acknowledgement. All right, there's a whole bunch of other. This is the data that's from outside. You don't have to remember this. It's good to recognize, but there is no need for it. This is, look at all the labels that are in there. That allows you to read the data. The checksum right here, this is what you look for to see if the data is good. We'll talk about that. Ethernet does that too. The sliding windows, the window size that we talked about, right? Just a minute ago, you send me 3 packets starting with number 3 or number 2, for example. All right, so this is the 3-way handshaking that I just discussed with you. UDP, we just discussed it. See, there's a lot less labels on UDP. It's the advantages of using UDP is fast, but the disadvantage is that it has no error connection, no unreliable, right? And there's no control on the transmission, no flow control. All right, now once those segments are passed to the network layer, who takes over? IP. IP operates at layer 3. So IP takes the segments or datagram, depending on who's giving it to them. And what it does, one of the first things that it does, it puts in the IP address, the source IP and the destination IP. Remember when we said on the last lecture that the source IP is given to you by the DHCP server, and the destination IP is given to you by the DNS server. Right? That's why we use the names. Also, there's a whole bunch of other labels that you put in on the packet itself. By the way, it becomes a packet. Once you start putting the labels on the segments, the whole thing becomes a packet. Now, IP doesn't do any connection. It doesn't call out to the destination to find where the connection is or the destination is or any of that. So it's considered to be a connectionless protocol. It's also unreliable as well. Here are this is the labels that are placed on the IP packet, IPv4 packet. Version, it's going to tell you that's a version 4, for example. The differentiated services, for example, that this is the quality of service, in case the number indicates if this needs to go first or later, depending on what type of traffic that's in here. If it's voice traffic, this number will indicate that this has priority, for example. What's another good thing? Time to live. This number starts with 255, for example. It's an 8-bit number. By the way, it's an 8-bit number. And it starts to dig down every hop you go through. If it reaches 0, then the packet is discarded. It gets thrown in the trash. So TTL is the number that tells the routers as they receive packets to route them if this packet is still routable or not. If a router receives a packet where TTL number reaches 0, then the router will throw the packet in the trash. Here's your destination and source and destination IP address. And here's the data. This is the segment from the top. Alright. You can go through all of these, in detail if you want to. Here's the IPv6 packet. You'll notice that there are less labels on an IPv6 packet. So therefore, the packet will move faster because routers have less things to look at. They'll leave it for someone else. Version, for example, is version 6. Traffic class is similar to the differentiated services. This is for quality of service. To set priorities to the packets. This is telling you how big the data is, right? Hop limit, how far it can go. And look at the address, much bigger address, right? All right, ICMP, the Internet Control Messaging Protocol. Now, IP by itself doesn't have any messaging control. Nobody really keeps track of where the data is flowing on the internet, if there's any errors, nothing like that. So ICMP comes in, he's like the manager that manages the interconnections. It tells you if there's any problems. So that's a separate protocol that runs at layer 3, and you may be familiar with pinging. When you ping something, for example, when your packet leaves your device, it has a TTL number on it, and that TTL number starts to decrement. When it reaches 0, every hop that you go through, the TTL number is decremented by 1. So if your packet just has an IP address, for example, on it, and that IP address doesn't exist, or the destination that you're trying to reach failed. So what you're going to do, the TTL number will eventually reach 0. So if I'm a router and I receive the packet and I decremented the TTL number to 0, I say, wait a second, this packet there is dead. So I take it and I throw it in the trash. Then the ICMP protocol that's running on my router, that where the packet went into the trash, will create an echo reply, because assuming that with the ping, and send that echo reply back to the sender telling that your packet has died. That's when you get the statement that says I'm down. And when I send that to you, to the sender, it's not going to take the same path that your packet came. It may take a different path. All you know is your packet failed. You have no idea where the packet died. Right? So pinging just tells you if the packet has reached the destination or not. And if it failed, you have no idea where between you and the destination failed. So to know exactly where it failed, what utility should you use? You either use traceroute if you are on the router, or you use tracer if you are on a Windows workstation. Right? Alright, so that is ICMP. IGMP, the Internet Grouping. Well, first of all, I want you to write down ICMP. Here's what I want you to write down. Just write down the first bullet. Right? And write down ping, which is an echo request, an echo reply is part of ICMP. Is a utility that is used in ICMP. IGMP, write this down. The Internet Grouping Management Protocol. This is really for multicasting. So if I want to send data to multiple users in a LAN, I have those multiple users be a member of a certain group on the server, and then the server will just send that data to them. If you remember, you'll get the data. It's usually used for video teleconferencing, video over IP. So, for example, if you have several users, just an example, I don't even know if they actually do that. But I think Verizon did that at one time. I don't know if they're still doing it or not. But anyway, if let's say several people in your neighborhood subscribe to HBO, for example, and they'll be a member of a specific group. They'll be given an IP address that starts with 254. Remember, that's class D. And then they'll get they'll send HBO on address 224. Whatever. And because they're members of that group, they'll actually get that. They'll get the HBO, and no one else will get it in the same area. So multicasting is used to send data to a group of users in a LAN. You can have a full course on multicasting. By the way, IPv6 only does multicasting. It does not do broadcasting. That's something else that you should also write down and remember. If someone asks you, what is, give me something that IPv6 does that IPv4 does not do, what you say, IPv6 eliminated broadcasting, and they only use multicasting. If you want to simulate broadcasting, just make sure everyone in the LAN is part of the group. They'll do it. And they'll get the message. It's just the same as broadcasting. So you don't have to have two things. All right. ARP, the Address Resolution Protocol. When you receive data, let's say I'm a router, and I received a packet. I put the packet in a frame. I put my MAC address on it, and now I need the MAC address of the device that I'm sending the data to in the LAN. So what I do is I send an ARP request, an Address Resolution Protocol. In other words, I'm saying, hey, whoever has this IP address, please send me your MAC because I need to send you a packet. So when I send this ARP request to everybody in the LAN, whoever has that IP address will send me his MAC address, his physical address. I take his physical address, I stamp it on the frame. Because the packet has to be encapsulated in the frame, and on the frame I have to have the physical address of the person who's going to receive it. So that's why I do an ARP request. I take his MAC address, I stamp it on the frame, and I send the frame to him. Actually, I send it to the switch. The switch looks at the destination MAC address. He knows where that person is located, at which port, and sends it to him. Right? If you want to get on the internet, by the way, let's say you're getting on the internet, what you're going to do is you send out, let's say you wanted to go to yahoo.com. Right? You got the IP address from the DNS server. You stamp it on the packet. Your packet is ready to go. You put the packet in the frame. You put your MAC address on it, but now you think that yahoo.com, the IP address is in your LAN. So you send out an ARP request to everybody in your LAN requesting the MAC address of yahoo.com IP address. So you say, whoever has this IP address, please give me your MAC. Nobody is going to respond in your LAN because yahoo.com server is not there. So when nobody responds, by default, you go to your gateway. That's why we call it the default gateway, your router, right? So by default, you are going to send an ARP request requesting the MAC address of your router, right? Your default gateway will give you his MAC address. You take it, you stamp it on the frame, then you take the frame and you send it to the default gateway, to the router. The router takes the frame, opens it up, pulls the packet out, looks at the destination IP address, and because he's got the post office, remember, and he says, okay, you need to go west. He grabs it, puts it into another frame, and sends it to another router that's located west and so on. So your packet actually travels from one frame to another frame as it traverses the network. So ARP, right, the first statement. It's a layered, actually the first bullet point, the second bullet point is good. The all 4 points. So please write those down. Alright? It's looking for an unknown MAC address. It knows the IP, but it looks for an unknown MAC address. Right? So here's a typical ARP. You can, by the way, go to Command Prompt and just type ARP space dash and the letter A. And it's going to give you your computer this is the cache memory in your all the different devices that are communicating with and send data to. And most likely, if you connect it to the internet, you'll have the IP address of your default gateway and its MAC address. You can verify that. Alright, so what do routers do? Routers so their number one job is to route data, to find the best path to the destination, right? They connect IP networks. right? Like zip code. Every zip code, every network, every LAN has a router. And these routers talk to each other, right? And they try to find the best destination. So that's what routers do. They are trying to connect LANs together, networks. And each network has an IP address, right? That's the number one job. So please write this point down. Routers can do the following: connect dissimilar networks, right? LANs together. They are layer 3, as we discussed it. Sometimes they do layer 4. They're trying to find the best path to the destination. Best meaning really the quickest, right? And then they reroute data. If there's a link, they're trying to find another path to get a destination. It's similar to a GPS system. So if you have a GPS system sitting at your location and you type an address, they'll find the best path. But you go from one hop to another, one router to another, right, to get to your destination. And depending on, this is a typical router, this is a home router, this is a mid-size organization router, enterprise, this is a big organization. They can act as firewalls too. So they can perform, they can filter out broadcast transmissions. So when you send an ARP request, that ARP request is only bounded inside the LAN. It doesn't leak into other local area networks because there has to be a router that will not allow this broadcast ARP request to go into other LANs. It can act as a firewall. It can act for remote access if you wanted to. You can send in your username and password and be able to come in. We'll be able to configure it as a VPN. They can do many other things, but its main responsibility is in routing data, finding the best path to the destination. Okay, so routers can actually route inside. That's called interior routers. Like, for example, when you have a big campus, you can have routers that route data inside a big, huge campus. You get border routers. They sit on the border that connects to the outside world, outside the campus. Like, for example, ISP, Verizon, or Comcast, or any of these companies, they have interior routers. And they may have a border router that connects to other ISPs. The exterior routers are the ones that are outside. They connect autonomous systems, like, for example, Comcast connecting one area of the Northeast to another area in the Southeast, or Verizon, for example. So it's the exterior router that really connects to the internet. They go from interior to autonomous systems to exterior. Okay. Now, what is a layer 3 switch? Layer 3 switch is a device that is similar to a router, but it does not do routing. All it does, what's the difference between layer 2 and layer 3? Let's just clarify that. A layer 2 switch only looks at the frame labels, the MAC addresses, and sends the data according to the MAC address. And you have to be inside the LAN. So layer 2 switches only works at layer 2 and looks at only at the labels that are stamped on the frame to get your data from one point to another. If you need to go to another LAN, like on a network, then you need a layer 3 device to be able to get into the packet that's inside the frame, because the packet is a layer 3, and routers can do that. So routers are considered to be a layer 3 device because they are able to get inside the frame, pull the packet out, and make a decision depending on what the IP address is. But the routers sometimes can be very expensive. If you need just a device to connect LANs together in your organization, to connect VLANs, purchasing a router may be an overkill. So what you can do is buy a layer 3 switch, which has the capability of getting inside the frame and pulling the packet out and connecting it to another LAN, and that's what you want it to do. So that's what a layer 3 switch is able to get inside a frame, pull the packet out, and reconnect and re-encapsulate this packet into another frame and sending it to another LAN. So That's the main, so that's what a layer 3 switch. So just because you can do that, we go to layer 3, and it's much less expensive than a router. But it doesn't, layer 3 switch does not do advanced routing protocols, like finding the best path to connect to outside LAN, like OSPF, EIGRP, none of that stuff. It doesn't have serial ports, for example, so it's a little bit less expensive. Layer 4 switch is really like a router that is able to look at the port numbers and act like a firewall. Okay, routers. When they receive data, they have a routing table, a chart that tells them which path the data is going to go to. Just like when a post office will send them a packet, you look at your zip code and you look at the chart. Where is the zip code located? It's located west. So it takes your package and sends it to a router that is west of him. And then that guy takes the packet, he looks at the chart, the routing table. So that routing table tells you to either send the data northwest to the exit ports. Typically the exit ports are serial ports on the router. So all you have to do is take the packet, look at the destination IP address, and then you look up the routing table. And hopefully that destination IP address is in the routing table. And then when you find it, you encapsulate it and send it out of that port. Alright, so here's a border router that connects to the outside wall. It's an interior router. It can route data for you. Here's the layer 2 switches that interconnect all of these devices together. Right? So all of these, this is the default gateway, right? For all of these devices inside of it. That routing table that we just talked about, you can actually type those routes in there in the chart, or you can have the routers themselves talk to each other. That's dynamic routing, and build their own routing table. Right? So write these 2 points down, the difference between static and dynamic routing. And also, what happens if you go through the routing table and, when the packet comes in, you look at the destination IP address and you look through every single entry in the routing table and nothing matched. Then you go to the last entry and it's usually the gateway of last resort. If there is no match, then you send it to whatever the gateway of last resort is. So the gateway of last resort is a router that accepts all writable messages if there is no matching. Alright, so here's a typical route command that you can use on a Windows base. On a Cisco router, you type show IP route. We'll practice some of this in class. If you take a Cisco class, we'll be able to do it. You'll be able to do this almost in every class that you can. Because we learn that this is how you actually find out if the router knows how to reach a destination or not. You've got to take a look at the actual routing table. Right? Routing metrics. How does the router know which is the best path to the destination? For example, if you use RIP, RIP, the Routing Information Protocol, counts how many hops you go to the destination and it will pick a route with the minimum hop count. So if there is how many routers you have to go through, in other words. A RIP uses the minimum hop count. This is called distance. How many hops you go through is called the distance. The more hops you go through, the longer the distance. So that's why we call them distance vector protocols. You may use bandwidth. OSPF uses bandwidth. Bandwidth is like the maximum speed limit. Well, I'll give you an analogy. For example, if you have a GPS that looks for the shortest distance, that's like RIP. The shortest distance may be, to go from one point to another, you may have to go through back roads to get to your destination. The speed limits are very slow. There may be a lot of traffic. But it's short, but it may take longer to get to your destination. OSPF, on the other hand, will say, okay, I don't want to use the shortest distance as my metric to get to the destination. I want to use highway speed limits. So I'm going to look for highways to get to my destination. I'm going to pick the highways that have the highest speed limit to get my destination. It may be a little bit longer, but most likely I'll get faster. So that is what theoretical bandwidth is a metric. EIGRP will say, well, you know what, I'll pick also bandwidth, the highway speed limit, but I also want to look if there's any traffic on there. I'll pick the route that has the highest speed limit with the lowest traffic. Traffic is like delay, right? That's delay. Load, how much traffic can it handle? Also, you can use that as a metric. The more metric you ask the protocol to use, the better the path will be, but the more time it's going to take to calculate the best path to the destination. RIP uses minimum hop count. OSPF uses bandwidth. EIGRP uses bandwidth and delay plus load and reliability too, how reliable the path is. So EIGRP is more reliable, and because it's more reliable, it has a lower administrative distance. So RIP has an administrative distance of 120, OSPF 110, and EIGRP is 90. If all three protocols were running on the router, all three protocols will find you different routes to the destination. Which one will the router choose? Is it the path that RIP chose? Is it the path that OSPF chose? Is it the path that EIGRP chose? It's going to choose the path that EIGRP chose because it has a lower administrative distance. Why does it have a lower administrative distance? Because it uses more metrics to calculate the best path to the destination. So therefore, you should never ever run more than one routing protocol on the router, because the router will pick the one with the lowest administrative distance anyway and ignore the others. So if you run RIP, OSPF, and EIGRP at the same time, you're just wasting memory and processing time, because your router will always pick the path that is chosen by EIGRP because it has a lower administrative distance. And these are the different routing protocols that we do. There's the ISIS, there's the OSPF, the RIP, and so on. We'll discuss more of these later on. The interior routing protocols are similar. They are used inside the border routers with autonomous systems. The OSPF, RIP, and EIGRP are interior routing protocols. Exterior routing protocols are BGPs, the border gateway routing protocol. This is the one that connects autonomous systems like the internet. All right. So write this down. IGP, interior routing protocol. There are distance vector protocols. Next to that, write RIP and EIGRP. Believe it or not, there's a distance vector. Link state routing protocol, OSPF and ISIS. Okay. For EGP, write down the definition, and BGP is really the only one that connects to the exterior routing protocol. Alright, so here's the autonomous system. You could be running OSPF here for the border gateway routing protocol here, and then BGP will connect this autonomous system with this autonomous system. Or could be EIGRP or anything. These are interiors, right? Interior routing protocol. We discussed OSPF, this is bandwidth. Nobody really uses intermediate system. OSPF is the most widely deployed routing protocol out there. And BGP is the border gateway, but this is the only exterior gateway routing protocol. When it comes to routing, when you take a Cisco course, we're going to spend a lot of time on routing, the interior routing protocols, and even BGP too. I don't know how to configure the router, set them up, test them, troubleshoot them, design a line behind them. So this is just for the information right now. All right, now the troubleshooting routing issues. So I know that I told you at the beginning of the class, in this lecture, that you're going to write a lot. So I want you to write down all of the different troubleshooting utilities and what they do. So we're going to look at netstat, nbstat, tracer and traceroute, and adapter. So netstat, well, you can actually write this in here, but what I want you to write down is I want you to create this chart. I want you to write all the different commands that are needed for netstat. So I want you to write netstat and the different parameters and what each one is. I know this is, if you want, you can take a snapshot of this from the, what do you call it? The PowerPoint presentation. So if you don't, but if you write it down, it's much better to write it down and create a chart. So I want you to know all of these. So you'll know, for example, at least even if you're going to make a copy of this from the PowerPoint presentation that I uploaded to you, at least read them. So I need all of those. And nbstat, write this down, provides the information of the net bias. We really don't use this, so we don't need to bother with nbstat. With net bias, that means you have a non-routable network, which hardly anybody ever uses. This is really an old legacy. So don't bother with this nbstat. Tracer or traceroute. Tracer, you use it on Windows. Traceroute, you use it with your router or Unix machine. Right? This is to find exactly the path. You use it to find out where your packet failed. So if your ping did not respond or failed, probably, and you want to find out exactly where the problem is, you use tracer or traceroute. So write these down. This will give you a good idea of how to use them. We'll have some exercises to do with traceroute and tracer as we move along. Path ping, this is an advantage of, to allow you to use ping and tracer together. So you can actually use ping to respond back to you and find out exactly where you get a little bit more information than just, your packet failed on the destination. Okay, so write these down and, and put the description of each you would do. And the ping command or ipconfig. The ifconfig is really used for in a Unix machine. ipconfig is used on a Windows machine. So please write all of these things. I know it's a lot, but it's important that you get familiar with all of these different commands. The more you use, the more often you use them, and you get familiar with the output of that utility, the better troubleshooter you will be. Okay, so interface errors. If the NIC card itself, sometimes if it's misconfigured, you may have a problem. If the cable is not connected properly, you may have a problem. So, two things that you could use. Always use the ping command to let you know if you are connected, and you can use the netstat command to give you a list of the interfaces on the device that can be used to troubleshoot the network with errors. So ping is probably the first thing you're going to go with first. If you think hardware failure, when a router, switch, or a NIC goes down, you probably want to use tracer or tracedown to track down where the problem is. So if you ping and you get a failure, it's probably in the path there's a router or a hop or a switch or something failed, with malfunctioning, not letting your data go through. You want to find out which one. You've got tracer, and it will tell you where the data stopped moving. Okay, to discovering neighboring devices, you can use the CDP on Cisco protocols. You know, they tell you who your neighbors are, what IP addresses they have. You may use ARP if you want, or the neighbor discovery protocol in IPv6. So please write this down. The IPv6 devices use a neighbor discovery protocol to automatically detect the neighboring devices and automatically adjust when neighboring nodes failed or removed. This eliminates the need for ARP and ICMP functions in IPv6 network. So there's a big advantage. There's no ARP needed, and there's no ICMP needed with IPv6 because it has the neighboring discovery protocol that does that automatically. Right? No ARP, no ICMP, no broadcasting, no NAT, no subnetting is needed with IPv6. Right? So preferable that you go with IPv6 if you have the choice when you're designing your own. All right. Remember, the black hole messages are being lost for no apparent reason. If you have your packets being lost for no apparent reason, so use the ping command to see if the frame is too large. Remember, we said the maximum MTU, the message transport unit, can only be 1500. So if your message is huge, it may not get to its destination. You can use the netstat command to display the routing table. For example, if you have a missing route in the routing table, it could be lost, so you want to track that to see if it's in the routing table or not, because if it's not in the routing table, it's never going to reach its destination. All right, so I know, please go through these, write down everything that I told you to do, especially, and also don't forget, you should have typed it down in here so I can see everything that you did, all the different commands that I asked you to do as well. All right, so until the next chapter, just keep up with the work. Good luck, and I'll see you then.